Hello, my name is Samuel Hui, and today I will be showing you how to do every part in Problem 2 of Exam 2. And the parts are just asking to find these quantities. So, just to recap, we have this mass 2 that's traveling in circular motion parallel to the base of the cone in perfect circular motion. I think I already said that, but anyways. And it's attached to mass 1, which is stationary and held above the ground. And whereas yeah. So, to start off, we need to draw our free body diagrams uh, to show how forces are acted upon either mass. So, mass 2, we draw a triangle like this, knowing that it makes an angle with the vertical called theta. And since we know it's traveling centripetal force, we have to set axes like this because centripetal force points horizontal. Now, knowing trigonometry and alternate interior angle theorems, we find that the forces that are acting upon the mass are shown, and that the vertical and horizontal components of each are like so. Well, that got messy real quick, but hopefully you get the picture. Fortunately for us, mass 1 is a lot easier than that, because the only forces that are acting upon mass 1 are just the tension force and gravitational force of m1g. So we can begin setting up our force diagrams. Let's just call this positive y, because why not? Get it? Since it's stationary, this becomes 0, which means that the summative forces are 0, which means that our tension force is equal to m1g. Now for this, let's sum up our forces in the x direction. Because in the x direction, the sum of the forces is equal to centripetal force of mass 2. Now let's think for a minute for what maximum velocity of a particle actually means. At maximum velocity, the particle is traveling around the cone so fast that there's almost as if there's no contact force between the particle and the cone, which means that the normal force may as well be 0. This simplifies to this, and we're left with a problem. We're left with both of the masses, and we can't have either of those masses in our final answer. Fortunately, we have the y direction to work with. In the y direction, the sum of the forces is 0 because, remember, the circular motion that the particle travels in is horizontal. So we're left with t cos theta plus n sine theta, minus gravitational force of the particle. None here. And we're left with this, which means that m1 is just equal to m2 over cos theta. Let's plug that into m1g to m1. We're left with m2 over cos theta g sine theta is equal to m2v squared over r. m2's cancel out, and we're left with v squared is equal to g r tan theta. Replacing r for L sine theta gives us this as our final answer. Cool. So now we got our final answer for part A. And moving on to part B. And going back to right here, we find that if we divide both sides by m2, we get that this ratio is proportional to v squared, or the velocity, which means that the inverse of this, which is what we want to find, will be inversely proportional to the velocity. Hopefully that brief explanation makes sense, and hopefully that means, if you've probably figured it out by now, that that just means that the bigger velocity, the smaller the ratio, which is what we want to find, and the smaller the velocity, the bigger the ratio, which is what we want to find in C. We'll get to that later. But anyways, since we already find our velocity, we can plug that in. Sorry for screwing up so much today. And we find that m2 over m1, by the way, tan theta is just sine theta over cos theta. Hopefully you remember that. And that just means that m2 over m1 is just cosine theta. Cool. Now we need to find the greatest that ratio could be, aka the smallest the velocity can be. Let's think for a moment again. So if you really think about it, the velocity of the particle can be as slow as possible and still maintain centripetal acceleration, and the slowest possible velocity would be a velocity that's close to zero. So this might as well be zero. And we have our normal force again. But what is our normal force? Well, let's go back to the y components of the forces acting upon particle 2. We get that our normal n sine theta is equal to m2g minus m1g cosine of theta, which means that this is our normal force. Now let's plug that in back here. We end up having that m1g sine theta minus m2g cos theta over sine theta plus m1g cos squared theta over sine theta is equal to 0. To solve for a ratio, we just move m1 to one side. My apologies. And m2 to the other side. Divide both sides by whatever is here, and divide both sides by m1. And we end up getting sine squared theta cos theta over sine squared theta, over cos theta plus cos theta is equal to the ratio. Let's combine both fractions, and we end up getting that sine squared theta plus cos squared theta over cos theta is equal to the ratio. And since this is an identity that just equals to 1, we end up getting that m2 over m1 is equal to 1 over cos theta, or secant theta. And that's our final answer for C.